Okay, here's one more example involving the rolling of dice, and then we'll wrap up the chapter here. Example 2 says if 6 dice are rolled, what is the probability that at most 5 sixes show? So we're rolling 6 dice, and we want to know how many of them show 6 on top, and we want to see what the probability is of getting at least 5 of those 6 dice to show 6 on top. So, very similar to last problem, we'll define a variable here. We'll call x is the number of sixes, and we want to know what's the probability of getting at most 5. Okay, well, at most 5, we could think about this a couple of ways, is less than or equal to 5. So we could say, well, that's the probability of getting 0 sixes. So we'd say the probability that x equals 0 plus the probability that x equals 1. We could get 1 6, or we could get 2 sixes, or you see this is going to be a little bit tedious here. Probability that we get 4 sixes plus the probability that we get 5 sixes. Any one of those possibilities would mean getting at most 5 sixes. So we could find all 6 of these probabilities and add them all together. That is an option. It would be perfectly correct. The other option is to say, well, the probability of getting at most 5, well, that would be the complement. The only way I don't get 5 is if I get all 6 dice to show 6s. So the probability of getting less than or equal to 5 is the probability of not getting 6. Similarly, the probability of not getting less than 5 is getting 6. All that to say, the probability of getting less than or equal to 5 plus the probability of getting all 6 to be 5s, if we were to add those two together, those are mutually exclusive outcomes. You can't have one without the other, and you have to have one of the two. They would add up to 1, right? The sum of all possible events must equal 1, which means that if you were to simply subtract the probability of getting 6 from both sides, then you would have the probability of getting less than or equal to 5. Okay, that's a bit of a long-winded way of saying that you could think of the probability of at most 5 as being 0, 1, 2, 3, 4, 5, or you could think of it as being not 6, or in other words, 1 minus the probability of getting all 6. Okay, so rather than compute 6 different probabilities, we can just compute the probability of 6, getting all 6 dice to show 6, and subtract that from 1, because getting 5 or less is the complement. And then we can just do our typical binomial probability. We know we're going to do 6 trials, 6 dice are rolled, and the probability of getting a 6 is 1 out of 6 on a fair die. The probability of not getting a 6 is 5, and we want to know what's the probability of getting all 6 to be 6s. So we want 10 not 10, we're rolling 6 dice. We want NCR, which is 6 choose 6, times the probability of getting a 6. We want to get all 6 of them to be 6s, times the probability of not getting a 6, which would be 5 sixths. And that would be raised to the 0 power because we don't want any of them to come up as not 6. So all we need to do then is type that into the calculator and we'll find our probability. So I have 1 minus 6 choose 6 times 1/6. Let's do 1/6 raised to the 6th power times 5 sixths raised to the 0 power. Again, if you want to be extra clear, it would do all of this operation before it subtracts the 1, but just to be extra clear, let's put parentheses around that probability. Inside the parentheses here, that's the probability that all 6 dice will show 6s. And then we get our probability is this kind of sassy fraction. If we're not sure what that equals, we can see that it's very, very close to 1 since they're very close to each other. And in fact, the probability ends up being 0.999979. Lots of 9s. So our probability that we would get at most 5 6s is 0.99979. Very, very high. Okay. Okay, and that's not surprising. If you roll 6 dice, you don't expect to get all 6 of them to show up as 6s. Okay, but the important point here is to recognize, okay, when we're doing these at most, at least problems, we want to think in the most efficient way, right? If we're saying at least 8 out of 10, well, let's just list 8, 9, and 10, find those probabilities. But if we're going the other way, in most of our scenarios, our successes are, or if we have a lot of possible successes, we might want to take the complement and say, well, rather than add up all the successful outcomes, let's just subtract the failing outcomes, the one where we don't get at most 5 6s. So be smart in how you go about doing that. If you had added up all these, you would get to the correct answer, so it's not wrong if you do it that way. It's just going to take a little bit longer. In respect to our notes, there is a calculator command in the Inspire calculator that can do these kinds of problems for you. You're welcome to study that and figure that out for yourself and use that on any exam. I'm not going to bother showing it to you since we don't all have the Inspire calculators. This problem right here requires the use of the calculator. So if we had calculators in class, I would go over it. It's a problem from AP Stats. It's beyond what you're going to need to do for this class. So as long as you know how you can go about solving at least and at most problems, you're in good shape. You don't need to go into the depth that this problem goes into. So in order to practice that, you can be working on these homework exercises on page 706 in your homework packet. Okay, that will be your last regular homework assignment. Then you'll do the review exercises, and then you'll be done. That ends our new content for the year. That ends chapter 16. Congratulations, you've completed the Advanced Algebra 2 course, and I can't wait to start teaching about pre-calculus and trigonometry in the fall. Alrighty, signing off.